Okay, so my name is Saurav. I'm a principal architect at the ONF, and I'm here to talk about a Trellis. So jumping right in. What is Trellis? So at its heart, it's a combination of three things. There is a data center leaf spine fabric that we consider as an underlay network. On top of that, there is a virtual network or a collection of virtual networks and the infrastructure that supports a collection of virtual networks that we call virtual network overlay. And this is based on VXLAN tunnels from one compute node to the other. And then both of these two networks, the underlay and the overlay, are controlled by a collection of applications running on top of ONOS, right? So we have SDN-based control on both overlay virtual networks using software switches and underlay fabric using hardware switches. And so this common control over overlay and underlay, this common SDN-based control, does give us certain advantages for doing a number of things like service compositions for tenants, doing things like distributed virtual routing, optimized delivery of multicast traffic streams, and so on. And so you can see from the examples that I'm giving over here, it has a lot of, it forms the heart of the network infrastructure in Cord, which you heard about in the morning. So all aspects of Cord, whether it's residential or mobile or enterprise Cord, they all run on the core Cord platform. And that core Cord platform is based on a network infrastructure that we call Trellis. So another look at it, if you've seen this from the talks in the morning, where the XOS is our service creation platform. Then there are a number of applications that run on ONOS, and then that controls your compute infrastructure as well as switching infrastructure. And then you can run VNFs. And then you have access equipment on one side, whether it's residential access or mobile access, different kinds of equipment. And on the upstream side, you have a metro network or a metro router. And so Trellis is this piece where both virtual switches and hardware switches form this overlay and underlay, and we interact with the upstream network, the upstream routers using this vRouter application. So together, that's what we call Trellis. So I'm going to focus on two of these aspects in this talk today. That is the hardware fabric and what we call vRouter. So starting with the hardware fabric, it's based on white box switches that we get from ODM vendors like Acton, or also known as EdgeCore. And I'm talking about a specific model over here of this hardware switch, which has 32 ports of 40 gig each. But there's nothing special about this configuration. There are people who have used 1 gig switches, they've used 10 gig switches, and 100 gig switches. When they have been trying out Trellis. What is special is the software that goes on this hardware is the same, irrespective of whether you're using it as a leaf, you're using it as a spine, you're using a different model of the switch with different speeds and feeds. The point is the software is the same. And what we use here is a collection of open source projects and open API projects. So let me start off with the hardware itself. That typically has a Broadcom ASIC inside it, either that, today that's based on Trident 2, but we're also doing Tomahawk switches, so both are available. We're also working very closely with Broadcom and an operator to try the Qumran version of their switches. And the operating system that runs on it comes from the Open Compute project. It's called Open Network Linux. There is a bootloader called ONI. But ultimately, you have to write software that allows you to program the ASIC. And what Broadcom has done is that they have published an open API that is known as OFTPA that exposes the features of this ASIC to an external SDN controller like ONOS via this piece of software that they have written called OFDPA. So you can stick an OpenFlow agent on it, and then the controller can treat the ASIC as another OpenFlow switch, but has all the features of the expo, or a lot of the features of the underlying ASIC exposed to it in terms of the forwarding tables and groups and so on. So with this infrastructure running in each switch, we have built a leaf spine fabric. And in this picture, as you can see, there are multiple data center racks with compute nodes. They're connected to a top-of-rack switch, and each top-of-rack switch is connected to the spines. And you see an ONOS cluster running over there with 3 ONOS instances that's actually controlling all the forwarding that happens in this fabric. So what's very important to understand is that we don't use any traditional networking protocols for the operation of the fabric itself. There's no BGP running in over here. There's no OSPF. There's no STP. There's no per VLAN STP, and all the variations that you find of data center fabrics when used in traditional networking. So this is a purely SDN-based fabric. And what you can see over here is the color. This is from the ONOS GUI, and what you can see is that the color of every switch over here represents the ONOS instance that is the master for that switch. So you can see that in this fabric, every instance of ONOS is a master for a different switch. And that's something unique to ONOS, actually, that you can not just, it's not just an SDN controller that is running in an HA environment, so that one controller instance is doing everything and the other is doing nothing. And then if the first one dies, then the other one takes over. In ONOS, every controller instance that is part of the cluster is actually doing work at the same time. So this is what we do, and there's a number of features that we have supported over time. Currently, we support bridging within a rack. So if any compute node wants to communicate with any other compute node in the same rack, that traffic gets bridged. We support access VLANs and trunk VLANs. When traffic wants to go across the fabric to another rack, that traffic gets routed. So this is very much an L3 down to the top of rack design that is common in data centers. So we support IPv4 and IPv6, which is an external facing feature. Internally, we use MPLS segment routing, but that's not something that's actually exposed to the end user. But that's how our fabric works. We do IP routing in the leaves, and we push labels, and the spines actually forward traffic on the basis of labels. We also support IPv4 multicast. So the traffic, a multicast traffic can be replicated inside the fabric. So you can see that the spine is replicating traffic down to a couple of leaves, and then the leaves again replicate the traffic to the destination nodes that have asked for that particular multicast group. We have lately supported DHCP relay applications, this time only for IPv4, but v6 is coming. And finally, one thing I wanted to talk about is a very important feature of the fabric, is that it allows you to treat the entire infrastructure as one big router, so that any external routers that we interface with can, the visibility that they have is that they are talking to one big router. Okay, and I'll talk a little bit more about that and why that is such a unique feature of this SDN control fabric. So, so typically, when people talk about an infrastructure and they say, oh, we need a router, they think vRouter, and then they say, okay, fine, you know, I used to have this router where I have a data plane in hardware, I have a CPU in there, or a CPU blade that's running all these control protocols, OSPF, BGP, and so on, and then there is some way to manage that router, either using the CLI, SNMP, so on, right? So now I need something, I need a VNF-based router, so I take the same thing and I make a VM where I have my data plane running in the VM, I have my control plane running in the VM, and I'm managing it from outside. And you will see many, many variations of this in the industry today by many, many different names, whether it's vCPE, vBNG, VP gateway, V lots of things. But they're essentially routers running in VMs, just like you had routers running in hardware. Well, then the obvious issue comes is that, well, if I have this running in my infrastructure somewhere, now all my traffic has to hairpin through this vRouter VM, okay? And well, so if I wanted to load balance things, I would want to have multiple such things, right? But now, if I have multiple such VMs with control and data plane stuck inside of them, well, then there's also the issue that my control plane is now getting more complicated. So this is almost a solution where, is begging for an SDN-based solution where you pull that control plane out and you use multiple data plane instances of that VM in order to be able to load balance traffic through it, okay? So we go one step more. It's very similar to the last one picture that you see, but we go one step more. We say that this is how our vRouter works, right? So our control plane is pulled out. So if we have to talk to upstream routers, what the underlay control does is that it tells this leaf switch that, hey, identify this particular kind of traffic, OSPF, BGP, so on and so forth, send it to Quagga or any other routing protocol suite, right? Once that information comes over there and say a peering session has been established, that information is then sent to the vRouter app. And any routes that are learned from the upstream router, the vRouter app programs that into ONOS, after which it's picked up by the underlay control application that programs the fabric, and then picked up by the overlay control application that picks up the virtual switches, right? So net, what this means is that in our solution, the vRouter is an application that is running just the control plane part, but this entire infrastructure is the data plane of that router, right? So it's a big distributed router, and that presents to the upstream network as one big giant router. And many people have told us, including operators, that this is a best-of-breed solution that a lot of people don't offer, or no one offers, actually, in the industry today. So having given that quick summary, I do want to talk very briefly about what we are working on right now, and that is data plane redundancy. Like I said, the leaf switch is a top-of-rack switch. If the leaf switch dies, then the entire rack goes. So obviously, we need two over there. And we're working on dual homing access equipment, dual homing upstream routers, and of course, the compute infrastructure that'll be dual home to these top-of-rack switches. So that's pretty big work that we're doing and will be available in the next release of I think the J release of ONOS. And if you want to have a look at the complete roadmap, there is a link in this presentation. You'll also find it on the Cord Wiki, and it'll take you to this Google Doc that talks about the features that we support, who's asked for it, whether it's a platform requirement or some of the operators that we are working with have asked for a certain feature, where is it available, what is it using, are there any issues, what are the features that are in the roadmap that we are currently working on, and the stuff that is there in the future. So this work, you'll find a lot of the work over here is being targeted towards a field trial that we're doing with an operator that'll start in July and will continue to the end of the year. That's all I had. Thank you, and any questions?
So what kind of analytics is on your roadmap to get from the fabric?
That's an interesting question because some time back we were using analytics specifically that comes with, on the Broadcom-based switches, we have S-Flow support. And we were exposing that to an external S-Flow collector that was doing some analytics to try and see are any of these leaf-to-spine links congested. And if they are, then they would close the control loop by calling an API on the Fabric control application that would say that, hey, this flow is pretty big on this particular link, and you move it to another of the uplinks to a spine that is underutilized. So we did that. That is very much a demo. It's not part of our release, but I think down the road we will make it part of, officially support it. And then there are a number of other things that operators do ask, and we'll be working on, some of which is supported in the hardware that we use, and some things might require. We do have plans to work with Cavium and Barefoot and use P4 in the future. But It's not on the roadmap right now, but analytics is very important.
I see two more questions. And Asim, I'm wondering if you want to swap in
Sure.
while we do a few more questions.
Sure. Just unhook it. Yes.
Two very simple questions. One is it using OpenFlow or something else? Second question is that how big is the spine and leaf?
How big is the, excuse me, what?
How many spine and how many leaf routers you have?
Yes, okay. So the answer to the first question, yes, it's using OpenFlow. It's using OpenFlow 1.3, which is one of the more recent versions of OpenFlow that does not have the issues that the earlier versions of OpenFlow had. So in the beginning of my presentation, when I talked about what Broadcom has exposed in terms of the API, the open API, it's called OFDPA. That stands for OpenFlow Data Path Abstraction. That allows you access to the bridging table and the MPLS table and the routing table and the ECMP groups and the multicast groups and the flooding groups and a lot of features of the aspects that you did not have with the old versions of OpenFlow. But with the newer versions of OpenFlow, and thanks to the work that Broadcom has done, we do have access to all that. So that was the first part of the question. The second part of the question was, how big is the fabric? How big can the fabric get? Okay, so it's designed to scale to 16 racks. Okay, that doesn't mean it does that right now. We're working on scale improvements. This particular deployment that I was talking about, or not deployment, the field trial that I was talking about in the second half of the year is targeted to use 10 leaves and 4 spines. Okay.
And I think there might have been one more question. But if not,
Speak up, we can hear you.
yeah, speak up.
All right, so you talked about, that the operator said that this doesn't exist, and you're quite right, it doesn't exist today. But for those that have been in the industry, will go back to the 98 to 2002, 3 timeframe when you had all these companies that were building these multi-terabit routers. The only difference was that we didn't have disaggregation then, so we had everything proprietary, but they were doing essentially the same thing. Have a distributed data plane with a centralized control plane in the manner that you pretty much just described. The Pluruses of the world were doing that right here in Silicon Valley.
Cool. That's good to know.
But it was all inside one big monolithic box, right? Well, maybe a multi-chassis thing. But essentially, we've disaggregated the network. And Trellis, Trellis is one of those projects that, to be honest, it's kind of hard to find and understand from our website presence and everything. We're doing so much at the ONF. I think it's a perfect project. It's one of the reasons I wanted to highlight it here. So more people understood it and knew it. It's an integral part of Cord, for instance, and I think it's a fantastic piece of technology.
And it's open source.
Oh, thank you very much.
Thank you.